In section 4.4 of the book, the author talks about organic contaminants in the soil. You'll notice this chapter is quite a bit shorter than the one on metals. That does not mean these are any less important, just he wraps them up a little more concisely. So I would like to call your attention on this slide to the table to the right first. When we're talking about soil pollutants, what exactly are we talking about? The author uses slightly different terms, whether they be European or older terms. They're not quite the same as the ones that are used standardly in environmental chemistry today in the US. So common soil pollutants that we have agrochemicals, so things like pesticides, herbicides, fungicides, things that are designed to break down quickly in soil but may leave degradation products in the soil that may or may not be an issue depending on the chemical. We have polyaromatic hydrocarbons, also known as PAH. And the major, now when I say source, this is not sole source, but this is a source, a major source for these materials in the environment. So a major source of PAHs is the incomplete combustion process, whether that be the burning of wood, waste material, combustion from an industrial process, something that does not complete the combustion. You will very often get these polyaromatic hydrocarbons. You can get polychlorinated biphenyls, or PCBs. These are not allowed anymore in manufacture and production, so you will not see those as much, but they are still there in the environment. There are still limited industries that get permission to use these, although they're not supposed to emit these. Where you saw a lot of these, there were a lot of industrial processes, but the manufacture of transformers and capacitors, things like that. One of the big ones you may have heard about was the use of PCBs as flame retardants in children's pajamas. So that was a huge issue. Mostly because these two especially, polyaromatic hydrocarbons, polychlorinated biphenyls, and then some of these others down here that we'll get to, are what we call bioaccumulators. So they build up in a biological system, be that plant, animal, human beings as animals. We tend to bioaccumulate those. They don't break down in our system. They just tend to build up in the removal system, such as the liver. You have organotin compounds. These are also pesticides and fungicides, slightly different class than the agrochemicals. And hydrocarbons and other volatile organic compounds, VOCs. And these are typically found from transport byproducts or solvents, but again, there are many, many ways to produce those. Now, I will point out, if you look, the author tends to use the term chlorohydrocarbons a lot. Chlorinated hydrocarbons. So those would fall under the volatile organic compounds. The volatile organic compound is a blanket term for a lot of those. So he specifies chlorohydrocarbons. So the figure that the author has provided here is an imagined or a contrived scenario. So he has imagined a site in Europe that has gone through many different stages in its lifespan. So in phase one, it was used for metalworks and for smelting. And so it had byproducts of rubble and blast furnace slag. This would have resulted in a buildup of heavy metals in the soil from that phase. And then he imagines that that phase ended, and so a new one was built, and it was a munitions factory. So the manufacture of weapons and ammunition, and this one would have also put heavy metals into the environment. It also would have put a lot of the volatile organic compounds in there. And he talks about a lot of the nitrogen containing compounds. So nitrogen containing compounds are very large in weapon manufacturing munitions. Things like nitroglycerin, nitroglycol, diglycol dinitrate, nitrocellulose, trinitrotoluene, TNT. Those are all going to be used in munitions manufacture, and those are going to have left behind volatile organic compounds. He then imagines that a gas works would have replaced the munitions factory at some point, and in his scenario, that was bombed during the war and was destroyed. So material from the gas works would have left the polyaromatic hydrocarbons, the PAHs. It would have left heavy metals. It would have left cyanides. It would have left phenols, which is under the volatile organic compounds. So it would have left a whole variety of these pollutants in there. And then he imagines that today this is a metalwork, and the metalwork, of course, is going to, possibly be putting metals into the environment. Also, the hydrocarbons, the volatile organic compounds. So a lot of VOCs going in there. And so you can imagine over time you're going to get this buildup. These chlorohydrocarbons are going to be emitted, all these other things, and they're going to eventually leach out into the groundwater. So storage tanks, former surfaces, you've got oil coming out of an old tank that was buried and left behind. So it's a very complex layering when you have these impacted areas, when you're trying to determine what's there and how they're affecting the environment. It can be quite a convoluted puzzle. So you have to try to deconvolute the history of the location that you're looking at. So again, here's just a flowchart looking at the pollutants, the organic pollutants here. So we're specifying organic now. Pollutants in the soil. They can go in a variety of directions. They can be volatilized into the atmosphere. They can, if they are on the surface, the sunlight can affect those and photodecompose those into other byproducts. You can have chemical reactions that go on that lead to the breakdown of those pollutants. There actually are a lot of microbes that can decompose a lot of these organic pollutants. Some of them do it quite neatly. It's a very interesting subject. It can filter, so solid substances can be filtered out before water leaches down to the groundwater stage. You can have it adsorb onto the surface of minerals. You can have precipitation going on. You can have the whole soil range going on here where you put it in solution with the soil and it can either be taken up by plants, which again, depending on the pollutant, is not necessarily a good thing. I don't know that you want PCBs in your corn, or it can be washed out into the groundwater. Again, not so good because then it ends up in your water. Or there can be erosion going on, which can lead to drifting and carrying of the pollutants throughout the atmosphere. So again, it doesn't just stay in one place. Once pollutants are in the environment, they tend to migrate about. In this figure, the author just briefly talks about the chlorinated hydrocarbons, which again here we're referring to volatile organic compounds, VOCs, in the soil atmosphere and how those can be distributed. And the basic idea here is that you can just sort of build up a 2- and 3-dimensional picture to trace them back to a point source. Now that is not necessarily an easy thing to do, but when we talk about soil atmosphere, we're talking about gases in the soil. There are ways to monitor gases in the soil. There are special probes that you can get that collect gases within the soil and measure them, and then you can use that to build a profile and trace these things back, because otherwise these can be notoriously hard to trace back to a source. Here the author looks at pesticides in particular in the soil. You can see here that the activity of pesticides is very similar to what he gave for just organic soil pollutants in the first place. So slight differences. You might have adsorption to soil colloids. Microbial degradation was already mentioned. So it's very similar. But basically what we're looking for in a pesticide in soil is one that will go through one of these breakdowns. So in other words, once you have it in the soil and you have it activated doing what it needs to do, it then kind of needs to go away. A pesticide is there to kill some sort of pest. Once it's accomplished that, you don't want it hanging around and creating problems. So if we look at conversion time curves for biocides, pesticides, things like that, what we're looking for is something that once it's killed the pest that's available, then it is going to, within a few days, reverse adsorb to soil particles. It's going to then break down in some way, attach to soil particles, decompose to CO2. Its bioavailability, okay, is only going to be for a short period of time. So the bioavailability should be high when it's applied, but then over time, as you go out in terms of days, weeks, months, that bioavailability should drop off, essentially go to zero at some point. So it's a huge issue to have these materials, volatile organic compounds, pesticides, fungicides, insecticides, to have all these in our soil, but how do we monitor those? And I know some of you for lab were asking, well, will we be able to monitor these things in the soil? Well, this figure kind of sums up why that's really not something you do in a quick afternoon lab. You're talking about a dedicated lifetime work for some of these things. So if we look at all of the substance we have, all the contaminants that we have, relatively speaking, compared to everything else that's in the soil, those contaminants are there in very small concentrations to start with. And there are so many things in the soil, there's no way we can know everything that's in every soil. So let's say that we can only identify 10% of the material in the soil. 90% of it is just unidentifiable. We can't trace it back. So we're going to aim for that 10%. Well, those materials that we put in the soil as organic compounds don't stay as organic compounds. They tend to volatilize or break down. That's about 9% of the 10 that we had. About 2% of that will be the chlorohydrocarbons, or the volatile organic compounds. Other volatile substances is another 6%, and then other readily volatile materials another 1%. So we're down to 1% other. Okay, and these are the things we're aiming for. Chlorophenols, PCBs, pesticides, fractions of a percent are going to be remaining in the soil. So in order to analyze for these in the soil, first of all, in order to analyze these, you have to know what you're looking for, because your technique is going to be very specific to that material, and how you extract it from the soil will depend on really what you're looking for and what other materials are in the soil. So you're trying to isolate them from everything else. First of all, they're in very small quantities. So if you think working on a microscale in an organic lab is tough, you should really try, extracting down to this level. So you're trying to identify those. You need to know what they are, and you need to have an idea of about how much you're looking for, so you know how to set up your analytical method. So it can be very, very difficult to measure these organic materials in any sort of impacted soil. That's why a lot of people tend to go more with monitoring rather than analysis, and just looking for effects from the material in the soil and just trying to keep an eye on that. And then in the last slide, he just talks a little bit about soil that's been contaminated with oil, and then the oxygen consumption of those materials in the soil. So if you remember the biological oxygen demand in water, it's a little bit similar to that, but basically it's the idea that we can look at the remediation or breakdown of oil in the soil based on oxygen consumption. So we're not going to go in a huge amount of detail into that, but the interesting thing about this is due to materials in the soil, bacteria that are called oil eaters, microorganisms that can basically break down that oil. And these have been used in with great success in not only soil but water areas where there have been oil spills. So when there's been a tanker that has run aground or sprung a leak and released all of this oil into the atmosphere, one of the ways to help remove that is to find these oil eaters that basically consume the oil and break it down into carbon dioxide and water eventually. That's what we end up getting to. So just a quick look at that, quick look at organic contaminants in the soil, and then we'll move on to the next section.